The last talk in this track is by Kirthi Krishnamurthy on image processing around us. Kirthi Krishnamurthy works as a software quality developer with Adobe Inc. in San Jose, California. She works on developing automation systems which verifies quality and performance for Adobe's flagship product Photoshop. Prior to joining Adobe, Kirti has worked as an image processing engineer for Facebook Inc. and a camera tuning engineer for Qualcomm Inc. At Facebook, she worked on camera tuning and calibration for the Facebook portal devices, and while in Qualcomm, she worked on the electronic image stabilization and camera tuning for drones that use the Snapdragon processor. Just as a context, this is the same Snapdragon 801 processor that is currently being used in the Perseverance rover that landed earlier this year on Mars. Kirti holds master's degree from Oklahoma State University in electrical and computer engineering. She has published multiple papers with Cornell University on cryptographic applications under the guidance of Padma Shri Dr. Subhash Kak. Welcome, Kirti, to this event, and I'll hand over the screen to you now.
Thank you very much. Thank you very much for the introduction. And let me present my screen. Just a minute. Are you able to see my presentation here?
Yes, it's visible now.
Okay. It's visible, right?
No, it's again gone now. This right now this Google Meet screen is visible from your end.
Okay. Just give me a second. Okay, now it is visible, right?
Yes, yes, it's visible.
Okay. Okay, so I'm talking today about image processing around us. So let's go to the agenda for today. I will be introducing what an image is, then the histogram of an image, then fundamentals of digital image processing. Then let me move on to the field applications, which consists of the commercial photography, medicine, and agriculture. I'll be just talking about 3 field applications and the question and answers. So what is an image? Anything that we see around us when we are decrypting in our brain is an image. It's a visual representation of objects around us. And it is defined by the mathematical function f of x comma y, where x and y are 2 coordinates horizontally and vertically. So every value of f of x comma y at any point will give the pixel value of that point of an image. So how is an digital image processing linked to the signal processing? This digital image processing uses the image signal. That is how it is a part of signal processing, and it uses the image signal. So in order to understand a digital image, you need to know three key parameters, which are pixels, matrix, and bit depth. So a pixel, this is the basic for any image. To define any image, you need a pixel, which is the smallest item of information in an image. Sometimes the resolution of an image also represents the number of pixels in an image. So when you say a 4K into 4K resolution image, there you are saying that you have a 4K into 4K number of pixels in that image. And a matrix. A matrix is a rectangular array of numbers, symbols, or representations arranged in rows and columns. We all know that. But a digital image is represented in the form of a matrix. So when I say f of x comma y, there x represents the rows of the matrix and y represents the columns of the matrix. The other key parameter which we need to know is the bit depth. The number of bits or pixels or binary digits per pixel is called the bit depth. So there can be multiple bits in of an image. So there can be an 8-bit image, a 16-bit, 32-bit, or a 64-bit image. The smaller the number of bits, you have lesser number of pixels, and the image might not be very clear because you have less number of information. But if you have a bigger image, say like a 64-bit image, then you have more number of pixels and you have more information, so the image will be more clearer for the visual representation. And you can see the below, this is the digital one of an image, a digital image, and here each of these numbers represents the pixel values. So you say that the value of the pixel here is 128. So how do we come to this number? So this number is obtained only between 0 and 255. The pixel values will be only between 0 and 255. So when you're telling a 128, then you're thinking that the pixel value is somewhere in between 0 and 255. So that is why you're seeing all the numbers here are the pixels of the image. Moving on to what a histogram is and why is it important for an image. So histogram is basically a representation of the image in the form of gray levels and frequency count. So it is like an X-ray scan of the image. So when you see an image, you don't know whether it is a bright image or a dark image. Histogram will help us understand whether it is a bright image or a dark image. So now here you are seeing that the contrast of this image is not that great, and because it is not very appealing for the user, right? Why is it not appealing? Because the histogram here, you can see that it is all clouded at the center and it is not distributed throughout the gray levels, which is 0 to 255. So if you distribute the gray levels throughout 0 to 255, then the image will look more appealing to the user. Here we do the same. We do equalize it around the gray levels, and you will see that image is more appealing. This is called histogram equalization. So now it's important for us to know what a contrast and a brightness of an image is. I have been talking about the contrast, the low contrast, high contrast. So what exactly is a contrast? So when we are talking about the contrast, we are referring to the pixels being less than, the values are closer to 0 instead of 255. So if you say that when I was talking about the pixel values being between 0 and 255, if it is closer to 255, it is a brighter image. So here you see that the image is very bright, right? So here it is closer to 255, and that is why you see a peak here in the histogram. And here it is a low contrast, wherein it is a dark image and values are closer to 0. That is why you see a graph which has a peak closer to 0 and not 255. So this is like a proper mid-range contrast images, all the three of this. So you can see the contrast varying for different brightness levels. So what is a bright image and what is a dull image? You can see here, right? You can see across the images here that this is not, the subject is not highlighted. So here you can see that there are certain rocks here which is not highlighted. Like the background is dark and this has made it more dark. So you are reducing the brightness here and you are making it more visible for the user. This is a brightness of the image, and this, because of the low contrast, this is the maximum brightness and contrast. So next, moving on to the fundamentals of digital image processing. So in order to know about digital image processing, these are the very basic fundamentals which any user has to know. It consists of image acquisition, image enhancement, image restoration, color image processing, wavelets and multi-resolution processing, image compression, morphological processing, segmentation, representation and description, and object recognition. So to know what exactly all of these does, I have few images here, like sample examples. Coming on, first moving on to the image acquisition. What an image acquisition is. This is an example of the image acquisition. Here we have a camera sensor, and the camera sensor is trying to extract this is a 3D object, like a scene or a 3D object, where the camera is trying to capture the data from the object. And it is converting it into an image, which is a 2D, which I mentioned that it will be in f of x comma y axis, right? X axis and a y axis. The process of the sensor extracting the 3D object and converting it into x comma y is the image acquisition part. So the next fundamental thing will be image enhancement. So what an image enhancement is, this is an example of the image enhancement. You can see that this is a MRI or a CT scan when you go to a doctor, how it will be visible, right? The bones and every muscle will be visible. So here we see that the parts of image are hidden here, and you are not able to see the details. So you need to perform the image enhancement to see these details here. And here you see that these lines which were not visible in the original image, it can be visible here. Thus, the image enhancement is the process of manipulating an image so that the result is more suitable than the original. The next fundamental thing will be, fundamental concept will be image restoration. So this is an example of image restoration. This is the original image and this is the restored image. So you can see that there are multiple blemishes on the face, and it is not, again, very appealing for the user, right? For any person who is viewing the image. You want to remove these blemishes. How does actually one remove these blemishes to obtain a restored image? So all of this has algorithms like machine learning algorithms, and machine learning and image processing algorithms are very closely related, and they are used hand in hand. But I cannot dive deeper into each of this because of the time constraint. But the model will actually read the pixels in this image, and it will learn through, say, machine learning unsupervised k-means algorithm. It will learn the model, and it will get to know that the pixels on the right side of the image and the left side of the image, then it gets to know about the blemishes, because the pixel values of these blemishes will be different from the pixel values of the other parts of the image. And that is how we can remove these blemishes, exactly like a content aware fill, where you're filling this area with the content of this particular area of the right side of the skin. Moving on to the color image processing, which is the next fundamental concept of digital image processing. So what a color image processing is, it uses the color of the image to extract features of interest in the image. So basically here you see a flower. This has all the red, green, and blue channels. Sorry. So here you extract the green channel. Basically, a color image will have just 3 channels. It will be either red, green, or blue. It will not be having any other, because all others are made up of red, green, and blue channels. So here, when you're extracting, coming back to the topic, when you're extracting from the green channel of this flower, this is how the image looks. And here you're extracting the red channel, and here you're doing the blue channel. So this is exactly the color image processing, where you're extracting like all features from different channels, and then you can either discard the red channel, or you want to add more green channels to make the flower look maybe more green. You need to add more green channels. You can just add another green channel here and do the image multiplication to get the final image. The next fundamental of digital image processing will be the wavelets and multi-resolution processing. This is an example of wavelets and multi-resolution processing, where you use various degrees of resolution in order to represent the image. And the next fundamental concept is image compression. Image compression, you can see that this is the original image and this is the compressed image. You can see that the compressed image has most of the pixels missing. This is because the compression reduces the storage required to save an image, and thus you will lose few pixels in the process. The next one is morphological processing. Morphological processing basically is you will keep the original pixels, original piece of information, and you will try to reduce the pixels or increase the other pixels. In this way, you're actually not losing the original content. You will only be losing the ones which are not required in the image, like redundant data, redundant pixels. So this is an example of the morphological processing. Next, moving on to the image segmentation. This is the example of the image segmentation, where an image can be segmented into multiple objects. So the object detection is one of the example of image segmentation. Whereas this is an example, I think the next one, image object recognition also. We'll get to the object recognition as well. So the object recognition actually recognizes the object. It not only detects the object, but it also recognizes the object. And the representation and description will be the last part of the fundamentals of digital image processing. So representation, you can see that the image can either be represented by the borders or the original image or the full image. So this is the way you can represent, either with a histogram or with the lines, however you want to represent the image basically. So learning about all the fundamentals of digital image processing, now we can dive deeper into the applications. the digital image processing applications in commercial photography. So Adobe Photoshop uses digital image processing in almost all of its, of course, the features, because it is based on the image processing itself. So I have listed few of the features, which consists of the select subject. I have an example here for the select subject where it actually selects the particular objects here. And another one is sky replacement. So you can see the example for sky replacement here. It literally selects only the sky part and replaces here. And it looks, it makes sure that the lake or whatever the data is, other than the sky part, is also reflecting the sky. So you can see the sky reflection here. And the next one is content-aware fill. This is the example of the content-aware fill, which I was explaining when during the fundamentals of digital image processing, where you select a particular content and you replace it with something else, or you can either make it with nothing, like you just remove the content, or you replace it with something else. And lens blur is another example with cropping and resizing. So you can see an example of the cropping here, where where you might lose certain pixels while cropping an image, and this is example of the lens blur, where you are blurring only the background, keeping the subject into account. So here it will check the focal length, and it will detect the nearest object, and based on that it will blur the farthest objects in the image. And next, moving on to the field applications in medicine field. So here we are representing this is one of the example where we are representing any MRI, or coming back to the CT scan or anything, in a 3D representation, where you are actually, you can clearly see what exactly is wrong. For example, if you're taking the CT scan of a heart, and there is a valve or anything blocked, and you're seeing with the 3D, you can clearly see where exactly it is blocked and how much it is blocked. And this makes the work very easier for the doctors to fix the issue or find a solution for it. And this is another example where in the breast cancer, you detect the cancer cells. So in order to detect the cancer cells, you are again seeing the pixels here. In the original image, you are seeing that this part of the image doesn't contain cancer cells, because the contrast of this, you can check the intensity of this pixel. It is less here, whereas this one is more compared to the surrounding pixels or the other neighbors. So you say that this has breast cancer where this doesn't have. And this is another example in medicine field. Here you can see that the MRI image of the brain is enhanced using image. The first one is image adjustment, and the second one is histogram equalization, and the third one is adaptive histogram equalization. So you can see the details of the brain here much clearer, right, with adaptive histogram equalization compared to histogram equalization and image adjustment, because this is using like a feedback loop in order to get the histogram equalized. Before equalizing the histogram, it is doing a feedback loop, and that is why this is much clearer compared to the other. And the next field application I'll be moving on to is agriculture. So in agriculture, you can use the digital image processing for recognizing different crops. Or here you can see that a mango will have a different kind of histogram, whereas the like a chiku or supporter will have a different kind of histogram. And here you are recognizing different leaves. You can like basically for any recognition or classification, you will need the classification of any kind, any plants or trees. If you want to classify, you will have to use the digital image processing there. And this is like a 3D map of the like a field. This one represents where you can actually harvest the crops, whether you can harvest in uh, area where there is less fertility and fertilizers available, or area where there is more. And this represents a, a leaf which has an infection. So here you have to recognize which leaf actually has an infection. Everyone cannot go and, like, people cannot go and examine the plants individually, right? But if they have the photographs, they can easily run it through the digital image processing and recognize which how many leaves are infected and which leaf is infected. So these are actually few applications of digital image processing. I would love to dive deeper into each of these, but because of the time constraint, I will have to cut down. And please let me know if you have any questions on my presentation. Thank you.
Thank you, Kirti, for this wonderful talk. So, Varki has a question. Yes, Varki, go ahead and ask.
Yes, thank you for Kirti for the presentation. It was very interesting. I just have a question related to your background because you worked in, I think in Qualcomm, you would have worked in processor side, and then now you're working in Adobe. So I just wanted to know how the difference is between working in image processing in the hardware side and in the software side. Is it more difficult to process in the hardware side, or is it easier to do it in the software side?
Yeah, it's actually a very good question. And I would say actually working in Qualcomm, I was working in Qualcomm as a video processing engineer there, and I was in the drones department. Yes, it was a hardware part, but we still need the concepts of image processing, because we, again, right, even if it is a drone or anything, we feed the image processing algorithms, we feed the image processing data into the drone. So obviously, like, the image processing part doesn't change whether it is the hardware part of or the software part. And yes, there will be some additions of learning about the hardware, learning about the software, but the concepts remains the same.
Sure, Kirti. But the computation, is it easier in the software side? When if you do
Yes.
for Adobe, it'll be easier, no? I think. Yeah.
Yes. So the computation is actually there in hardware side as well. For example, in drones, when I was working in Qualcomm, right? So my work was to check the work on the like electronic stabilization of the video. So there I had to see if an image is actually blurred or is it clear when you take pictures from the drone, right? So in that way, again, I have to dive into the image processing. I can't examine each image individually. So software was involved there as well as here. Yes, but in Adobe, like, there is more software and algorithms involved compared to the Qualcomm. Yeah.
Okay, thank you.
Any more questions from the audience? Okay. So there doesn't seem to be any more questions.
Thank you for
so thank you, Kirti, for this Yes, it was indeed our pleasure to hear about image processing and its practical applications. Kindly accept this plaque as a token of our appreciation from IEEE-IISc ComSoc. Thank you.
Sure. Thank you very much.